At 2:14 a.m., the system failed. Not catastrophically, not with alarms or explosions. It just stopped responding. A hospital network in the Midwest, patient records frozen, medication schedules inaccessible. Nurses switched to paper. Doctors started making decisions without full histories. One nurse paused in front of a screen that wouldn't load. She wasn't thinking about infrastructure or distributed systems. She was thinking, do I have enough information to treat this patient safely? The IT team was called in, then more engineers, then specialists. They traced the issue through layers of software, interfaces, dependencies, until they reached a part of the system no one fully understood. Not because it was hidden, but because the people who built it were gone. And the people maintaining it had only learned how to work around it, not through it. This wasn't an isolated failure. It was a symptom, a slow shift happening across the digital world, a shift some are beginning to call the Great De-Skilling. For most of human history, tools extended our abilities. A mechanic understood his engine. An engineer understood the system they built. Understanding wasn't optional, it was the foundation. But over time, something changed. We began to prioritize speed, convenience, abstraction. We stopped asking, how does this work? And started asking, does it work? You can see the consequences of that shift in moments that, at first, seem unrelated. In 2018 and 2019, two Boeing 737 MAX aircraft crashed. A software system designed to assist pilots behaved in ways they didn't fully anticipate. Pilots were trained to trust the system. Engineers had layered automation on top of complex control logic. But when the system failed, something critical was missing. Not just information, but intuition. The deep, practiced understanding of how the aircraft should behave under stress. Automation had worked until it didn't. And when it didn't, the gap between system behavior and human understanding became fatal. In 2021, Facebook disappeared from the internet. Not partially, completely. A misconfigured routing update disconnected its own infrastructure from the global network. Internal tools went down. Communication systems failed. Even employees couldn't access buildings. What followed wasn't immediate recovery. It was confusion. Because the system wasn't a single system anymore. It was layers of automation, networking, and dependencies that no single engineer could fully see at once. The people responsible for fixing it were highly capable. But the system itself had outgrown any one person's understanding. And then there are the systems that never left. Large parts of the US government still run on COBOL, a programming language created in the 1950s. It works. It has worked for decades. But very few engineers today know how to write it. Fewer still know how to safely modify it. These systems persist not because they are well understood, but because they are too critical to touch. They are maintained through caution, not comprehension. This is the pattern. Not failure, but fragility. Modern systems are built on layers. A typical application depends on external libraries, cloud infrastructure, APIs, and services written by people in different companies, in different countries, at different times. Each layer works, until it doesn't. And when it breaks, the process isn't simple debugging. It's descent. Through layers of abstraction, through assumptions, through code no one in the room originally wrote, until eventually you reach a point where progress slows. Not because the problem is unsolvable, but because understanding is incomplete. At 2:14 a.m., that nurse was still waiting. The system hadn't come back. Engineers were working. But from her perspective, nothing was happening. This is what managed complexity looks like from the outside. Everything works until it doesn't. And when it doesn't, the recovery is no longer predictable. This isn't just about infrastructure. It's about how we build. There was a time when engineers were trained to understand systems from first principles, memory, execution, failure modes. Today, a different model is emerging. one built on tools that accelerate development, and none more influential than AI. AI-assisted coding tools have changed how software is written. Developers can now generate functions, entire modules, even full applications in seconds. They can move faster than ever before. And most of the time, the code works. But speed comes with a trade-off. Because when you generate code, rather than construct it step by step, your relationship to that code changes. You review it, you test it, you integrate it. But you may not fully understand it. This creates a new dynamic. Developers are no longer just writing systems. They are curating them, assembling outputs from tools that operate at a level of abstraction far above the machine. And this works until something breaks. Because debugging requires something different than building. It requires mental models. It requires tracing cause and effect across a system. It requires understanding not just what the code does, but why it behaves the way it does under stress. If a developer cannot reconstruct the logic of a system without the tool that generated it, then their ability to fix that system is limited. Not immediately, but eventually. AI doesn't remove skill, it shifts it. Toward speed, toward orchestration, away from depth. And at scale, that shift matters. Because systems don't fail at the surface, they fail in the details, in the interactions no one predicted, in the edge cases no one fully explored. Now combine that with everything else. Legacy systems no one wants to touch. Global infrastructure built on layered dependencies. Teams inheriting code they didn't write. Tools generating code they don't fully understand. What you get is not instability, you get something more subtle, a system that appears stable, but is increasingly difficult to repair. This has happened before. In 2003, a power line in Ohio brushed against overgrown trees, a relatively minor event. But due to failures in monitoring systems, communication breakdowns, and cascading dependencies, that single event triggered a blackout affecting over 50 million people across the northeastern United States and Canada. Operators didn't see the full picture in time, not because they weren't trained, but because the system itself had become too interconnected to manage intuitively. Failures propagated faster than understanding. That is the risk. Not that systems fail, but that they fail faster than we can comprehend them. So what is actually at stake? Not just efficiency, not just reliability, but agency, the ability for humans to step in, understand a system, and bring it back under control. At 2:14 a.m., that nurse didn't need perfect software. She needed enough understanding in the system behind her, that when it failed, someone could fix it, quickly, confidently, completely. The direction we're moving in makes that harder. Not because engineers are less capable, but because the systems they are working within are becoming less transparent, less knowable. This doesn't mean we abandon abstraction, or automation, or AI, but it does mean we need to be deliberate. Engineers need to understand the systems they depend on, not just how to use them. Organizations need to prioritize maintainability over speed in critical infrastructure. And there needs to be space for deep expertise to develop, not just rapid output. Because if we continue to optimize only for speed, we will eventually reach a point where systems can be built faster than they can be understood. And when those systems fail, recovery will depend on knowledge that no longer exists. So the question isn't whether systems will break. They will. The question is, when they do, will there still be people who understand them well enough to fix them? Or will we be left managing failures we can't fully explain, standing in front of systems we can't see through, making decisions without clarity? At 2:14 a.m., the system eventually came back, but not because it was fully understood, because the right combination of fixes worked. This time, and next time, when the failure is deeper, when the dependencies are more complex, when the knowledge gap is wider. What happens then? We didn't just build machines that think, we built a world we no longer fully understand.